introduce Ronitt. Ronitt is one of the organizers of the special focus sublinear algorithms overarching session. So we're very grateful for her to convene myself and the others to organize this workshop. So thank you for the support, and you're going to tell us about sublinear time algorithms and learning.
Oh, this was the title.
Yes.
Yeah, that's what I'm going to talk about. Thank you for inviting me to the workshop. But I guess as you can see, it was like a soul day situation. Okay, so I'm going to talk about two stories in the connection between sublinear time algorithms and machine learning, or at least computational learning theory. And the first I'm going to talk about is how to safely use distribution-specific learning algorithms via sublinear algorithms. And that's work with Arsen Vasilian, who's currently paying for my lunch. But I'm a bad advisor. Okay, and the second is how to convert learning algorithms into proper learning algorithms via sublinear time algorithms. And that's with Jane Land back there, and also Arsen. Okay, so I'm going to start with testing algorithmic assumptions. And here's the basic paradigm that we want to talk about. Some algorithmic tasks are hard in general. Okay, so, but they may be easier for specific input distributions. Right, so maybe you have an algorithm that works really well when your data is from the uniform distribution or from a Gaussian distribution. But if it's not, then who knows? It may give you the wrong answer, or it may be very slow. It's not clear. Okay, so how do you know if you can use this faster algorithm? In particular, this is fast. Okay, how do you know whether your inputs actually come from that assumed input distribution? Okay, so that's the question we're going to talk about when we're going to focus on a specific paradigm in machine learning that relies in an essential way on distributional assumptions. Okay, and that is agnostic learning. Okay, so let me define normal learning, and then we'll define agnostic learning. Okay, so what's normal? I think this is like standard learning. So in standard learning, you're given some examples, and they're labeled. So you're given inputs xi and the function value g of xi. The xi's are assumed to be IID, and the g is assumed to be an unknown function in some concept class, which we'll call script f. Okay, and what we're going to talk about today is the question of learning half spaces. Okay, so in this case, the functions are all f is the class of half spaces, say in Rn, but it could also be over 0, 1 to the n in the Boolean case. And these functions are defined by some hyperplane, and the function value is 1 on one side of the hyperplane and 0 on the other. Okay, so the concept class f is all hyperplanes. I mean, is all half spaces defined by hyperplanes. All right, now what's the goal of the learner? They see these examples, xi, f of xi. And now you have to come up with your attempt at guessing what this line is, what this hyperplane is. And so you're trying to find some f, and you may not be perfect, but you want to find some f that has small error compared to the actual g that is being used to label these examples. Okay, so it's okay if you're a little bit off, because you might not be perfect. So here's this green one was g, the blue one is f. It mislabels a couple of points out of all of these examples. That's okay. So you just want to find an f that has small error. You're given some input epsilon, and you're supposed to have error less than epsilon. Okay, and the error is defined as the probability that f of x does not equal g of x. All right, what is agnostic learning? In agnostic learning, you're still given labeled examples, xi, g of xi. Now you are not told that g is from this hypothesis class. Okay, so g may not be a half space. What you need to do is you need to find the best half space you can to fit this data. Okay, so you want to find the best one, and you're going to compare what you'd like is your error to be no more than opt plus some additive error epsilon. That's agnostic learning. Or maybe some constant times, some multiplicative error, maybe 3 times opt or 2 times opt or 1.5 times opt plus this additive error epsilon. So that's called, when c is greater than 1, it's semi-agnostic learning. Okay, and opt is just the best you can do within the class of half spaces. All right, so that's what we need, because like this models the case where you have noise. When do you not have noise? Or maybe the concept class is close but doesn't quite fit, so that's another. And this is like adversarial noise, not just random noise. So this is really what we want to do. So why isn't that what we actually do? Okay, so the reason is, in terms of samples, we're okay, we can do it. But in terms of running time, there's no 2 to the little o of n runtime algorithm known, where n is the number of dimensions of this space. Okay, so that's why we can't do it. Furthermore, it's not just that we don't know, we actually have computational hardness results. Okay, so we know this is hard in general. All right, so
under which distributions?
So far everything has been distribution free. Okay, you need to, for a second, I'll let you ask that question in a minute, okay? Okay, all right, so now the question is, are we sunk? Okay, so is this like, should we just go home and be done with agnostic learning? We can't do it. And the answer is no, because, now ask your question. Now ask your question, under which distribution? Because there are efficient agnostic learning algorithms with distributional assumptions, okay? So that's why we care about distributional assumptions. So this is supposed to motivate that we need to know that our data satisfies certain distributional assumptions, okay? And one example would be data comes from the uniform distribution. Okay, so there are lots of works. These are some examples of works in agnostic learning that use distributional assumptions and show that under those distributional assumptions, you can learn something, okay? So coming back to our main question, in a setting where distributional assumptions are crucial, how do you know whether the data actually satisfies those distributional assumptions? All right, so you might say, I don't need to know. I actually don't care if I know. I will just run the learning algorithm, and then I'll estimate the error of the learned hypothesis. And if it's small, great, who cares? You know, like it doesn't matter if the data actually satisfies that distributional assumption, because it worked, right? So that would be one approach. The only problem is if the error of the learned hypothesis is not small, then you don't know, is your distribution assumption wrong, in which case you need an algorithm that works for a different input distribution? Or is the best hypothesis in the hypothesis class pretty bad, in which case you would need to come up with an algorithm, a learning algorithm for a different hypothesis class? Okay, so that's the question. And how can you tell whether it's A or B? I just want to point out that you don't need to, in the realizable learning case where you assume the first, what I called normal learning on the first slide, where you assumed that the data was generated according to a half space or like something in the hypothesis class. Case B never happens. We assumed this was 0. So if you didn't learn well, you always know the distribution assumption is wrong. But here, we're in the agnostic learning case, and here we don't know what is the optimum error, and we have data, we have a hypothesis class, a concept class, and what is the best error? I don't know. So is there some way that we can rule out case A? Okay, so I don't know how to tell if we're in case B. So maybe we can at least rule out case A. Okay, so that's kind of the goal here. All right, so we want to test distributional assumptions for agnostic learning. And here's some challenges for distribution testers. One is whether it's sufficient, because when you test whether data satisfies a certain distribution, you're guaranteed to pass data that actually satisfies the assumption. So if the data, for example, if you're assuming uniform, and the data really is uniform, then the tester has to pass uniform distribution. And you also know that your tester has to fail epsilon far from uniform distribution, but in the middle, there's no guarantee what the tester is going to do. So the tester may actually pass slightly imperfect distributions. Okay, so that could be one problem. Maybe the agnostic learner doesn't work with slightly imperfect distributions. So you have to figure that out. And the second thing that's actually much more problematic is the issue of sample complexity. We know what the sample complexity is for testing uniformity, identity, independence, all these things with respect to L1 distance. Gaussianity, we know everything. And the good news, there's some good news, you need fewer samples than what it takes to learn the distribution. And that's good because learning the distribution requires a number of samples that's linear in the domain size. And if you have an n-dimensional data, then it's at least 2 to the n. It's going to be exponential in n. So being better than 2 to the n is good. The problem is it's still 2 to the omega n, because we're going to get it down by a square root of the domain size, but square root of 2 to the n is 2 to the n over 2, so that's not very good. Okay, so this is really a non-starter, because in our example of half spaces, we're not going to take 2 to the n over 2 samples to then use an agnostic learning algorithm, which only needs n to the order 1 over epsilon samples. Okay, so I mean, we would then prefer, we would prefer to use the really bad algorithms that I talked about before that have horrible running time.
Aren't we stuck? Because in some sense, if we can tell that we're not in the uniform distributions, and we made a test. So, and we have a lower bound for the test, so it seems that like...
Okay, so let's see why we're, okay, good point. Maybe we're stuck. Maybe we're just stuck. There's nothing to do. Okay, so what we're gonna do is define something called a tester-learner pair, which is gonna perform something weaker than testing. Okay, so we're gonna think of the tester and the learner as a pair that come together. The tester is specific to the learner. Okay, if the tester passes the data, okay, what we want to say is if the data satisfies the assumption, the data really is uniform, the tester should pass it. However, the tester may pass other things. It might look good to the tester even though it's completely not uniform. Okay, if the tester passes the data though, it better work with the learning algorithm. Okay, so we're going to test something weaker, and you'll see an example where it'll be clear what you can do. All right, so we show, so this is work with Arsene Vassilian, who finally finished paying for my lunch and has now joined us. He's a, thank you. So we show that we can test tester-learner pairs for decision lists over the uniform distribution on n-bit vectors, half spaces on Gaussian and uniform, and all these runtimes are much less than 2 to the order at theta of n. And in fact, these sample complexities are very close to that of the agnostic learner on its own. So you don't pay much for being certain that it actually came from the right distribution. Yeah.
So did you have to come up with a new learner, or did you use existing learners and just testers?
So that's a really good question. Did we have to come up with a new learner? And I'm not sure that in general, in this first work, we did modify the learner. And then in at least one of these cases, we had to modify the learner slightly. And it's also not true that just every single agnostic learning algorithm for one of these problems works with our tester. So the tester works with one of the learners. Okay, and it's, so just one has to be really careful. It's really a pair. But I don't think that always you have to modify the learner, but maybe Arsene has something to say about that. Where are you?
So is it true to interpret that even though the assumption was that, for example, you have the uniform distribution, you actually need a much weaker assumption?
That's going to be the point. Okay. So a helpful idea is it might be enough, instead of testing that your distribution is uniform or Gaussian, why don't you test moments of the distribution, or like the low order moments of the distribution, and make sure it matches. Okay. So one example for uniform distribution, let me move to uniform distribution over n-bit vectors. We're going to use k-wise independence. So a distribution over n-bit vectors is k-wise independent if when you look at any k bits of the vector, you get uniform distribution. So I have this, I'm getting samples, each time I'm getting n bits at a time, but I only look at a certain fixed collection of k bits from all of my samples. The distribution is going to look perfectly uniform over those k bits. Okay, that's k-wise independent. It's much weaker than full independence. Now, testing full independence takes 2 to the n over 2, but we also know that testing k-wise independence is something like n to the theta k. And we're going to need k being something like log 1 over epsilon. So this is going to give us a runtime, a number of samples that's n to the log 1 over epsilon. So k-wise independence for these parameters is a lot better. Okay. So it's easier to test. So we're going to use something weaker than independence. It's easier to test, but you need to check that the learning algorithm doesn't somehow rely on complete independence, okay? And this is a little tricky because it could be that there are k-wise independent distributions for which the optimum answer for the agnostic learner is very different than for optimum on the uniform, okay? So it may be that you can do a much better fit on k-wise independent distributions than uniform. or much worse. And so there's a connection here to pseudorandomness. It must be the distributions that pass the test somehow fool the concept class. Okay, and this is very high level, but it can be made more specific. So one thing that, okay, so I just want to mention the algorithms used here also work for the agnostic learning algorithms. These paradigms can also be used to learn monotone functions and convex sets. These are works by, I think I dropped the full thing here, but okay. So there's a whole paradigm here. And these same algorithms, the very same algorithms can be used to learn monotone functions over convex sets. You would just run them longer. You would run them for 2 to the O tilde of square root n instead of 2 to the log n, or 2 to the log 1 over epsilon. So it's exactly the same low degree polynomial regression, but it doesn't work for monotone functions or convex sets. While the agnostic learning algorithm can be 2 to the O tilde square root n, the tester-learner pair in both cases needs 2 to the omega n. Okay, so these do regression on degree root n polynomials. So you need to learn all the root n polynomials, and there's n to the root n of them, which is 2 to the O tilde root n. But it's not enough to just learn them and do the regression. And the reason is because there's no fooling in this case. Okay, things can be very different if you had k-wise independence compared to full independence. All right. Okay, so since this work, there had been, this came out like, it was published a year ago, but it was actually put on archive before that. So since then, there's been quite a bit of excitement in this work. There was a work by Golakata, Kothari, and Clivens, which is really beautiful. It's gives more efficient tester-learner pairs. It does more concept classes like intersections of half spaces, constant depth circuits, decision trees, more distributions, for example, strictly sub-exponential. And then they elucidated this important connection to pseudorandomness in this work. Okay, it was also there before, but it was really made clear here. Okay, and then since then, there have been more works that give fully polynomial sample testers for semi-agnostic learning. If you remember, we had a log 1 over epsilon in the exponent, so these get rid of it. It's polynomial both in n and 1 over epsilon for semi-agnostic learning, which is not actually possible for agnostic, but these guys get it. So this is a series of works, and they also, lots of different ways of extending the works to more types of distributions and classes of distributions, even if you don't know which one in the class. And what I want to mention is some very recent work by Clivens, Stavropoulos, and Vassilian is handling the problem of distribution shift. Okay, so this is like a really big problem in machine learning. What happens if you train on one distribution and then you need to use the algorithm on another distribution? So this is something that there are like workshops at ICML about this, and so how do you know that the training and testing distributions are close enough for use by the learner? Okay, so these Clivens et al. Give a framework which either says you can do good learning or it detects a distribution shift. Okay, so it's a way of testing the data good enough for the algorithm, and you know that you can either safely use it or there's been a distribution shift. Okay, and now there's something really new. It's really hot off the presses by Goel, Stavropoulos, Shetty, and Vassilian that handles a tolerant case. So even if there's been a little bit of a distribution shift, it guarantees that it still passes and lets you use this data. It figures out how to let you use this data if there's only been a little bit of distribution shift with your learning algorithm. But if there's been too much, it alerts you that there's been too much distribution shift. Okay, so this is all very new. Okay, so I spent 25 minutes on the first half. But I still want to talk, okay, so there's open questions. Let me skip the open questions because I want to talk about the second half, at least say a few words about this. Okay, so this is joint work with Jane and Arsen on properly learning monotone functions via local correction. And so I just, so I'm going to unpack the title. So monotone functions, I think we're probably pretty clear on. Just remember that these are n-bit numbers, and we're saying that x is less than y. This is now the domain. not the function. But the domain x is less than y if at every bit xi is less than or equal to yi. So this is like the arrows point that this is less than this. And the function respects this partial order of the domain. So f is monotone if when the domain element x is less than y, then f of x should be less than or equal to f of y. Okay, so so that's what we mean by a monotone function. And these are kind of functions that have been studied widely in testing and learning. So lots of people have looked at them. They have importance, for example. Okay, so I'm not going to talk about how important because I'm running out of time. So I'll talk about this. Okay. Okay, so what's the proper learning problem? So we talked about learning before. Now we're going to talk about monotone functions. So you're given samples xi, g of xi, where g is some unknown monotone function. And we're going to assume the xi's are a uniform distribution. And our goal is to find a description of the monotone function g. Okay, so we're going to output g hat that's epsilon close to g, meaning that they disagree on at most an epsilon fraction of the domain. All right. And what we'd like, okay, so up to here, that's normal learning. Okay. What makes it proper is we want g hat to also be monotone. We want g hat to be from the same class that we're assuming that g comes from. Okay. And so often people want these proper learning algorithms. For example, if you're trying to understand the decision list that doctors use to prescribe medication, you may want to learn a decision list by another decision list, even if it's slightly different from the one the doctor uses, but it's close enough. Okay, so it's one of the reasons people give for being interested in proper learning algorithms is explainability. Also, they're useful in lower bounds. And actually, improper learning for monotone functions, we've known how to do since 1996. The work of Bashuti-Tamon gave an improper learning algorithm that had sample complexity 2 to the O tilde square root n. Okay, so that's a lot less than 2 to the n. And there's reason to believe that's the best you can do. Okay, so they get examples, and this is over uniform distribution, by the way. So they get examples of xi, g of xi. The learner looks at it and outputs a g hat, which is close to g, but it's not guaranteed to be monotone. Okay, so this is like my picture of a hypercube, and it's not monotone, but it's close to g. All right, and the runtime is 2 to the O tilde square root n. Okay. All right, so this is improper learning, and it turns out that for proper learning, the sample complexity is the same because we can just use Bashuti-Tamon, and then we can take the output of Bashuti-Tamon and find the closest monotone function, but we don't know how to do that in 2 to the little o of n running time, okay? Because the output of Bashuti-Tamon, we can write down all the input-output functions and then find the closest monotone function, but that's a problem that's already the input to our problem is 2 to the n. So we don't know how to do that better than 2 to the little o of n time, even with queries. And what we're going to give here is a 2 to the O tilde root n time algorithm, which is essentially optimal because there's a lower bound of 2 to the omega tilde root n for learning in general of monotone functions. Okay, and the thing that we're going to use, so if there's anything you remember, is, so the next slide is, okay. So what we're going to use is this notion of local property correction, okay? So the idea is the function is supposed to have some property, such as being monotone, and we want to locally fix it so that it has the specified property. What that means is I want to provide query access to this function where I can fix it without going through the whole function and finding the closest monotone function. Okay, so I'm going to make a query like, what's the value of f of x? And it's going to tell me 0 or 1. And then I might ask about f of y, and it's going to tell me 0, 1. But if at the end I asked about every single location, whatever came out should be a monotone function. And moreover, the person I query has to wipe its memory completely between queries, so it cannot remember past queries. Okay, so whatever it has to do has to be consistent with itself without knowing what I'm going to ask about, and it's not building itself up dynamically by remembering my queries. Okay, so people have done this for linear low-degree polynomials, monotone functions, and I think this particular model was first mentioned in Elon et al. And Sachs and Seshadri, this local property correction. And and there have been several works on doing this. So far, previously to this, fixing monotone functions locally required exponential dependence on the dimension. And I want to mention also for Lipschitz functions, there's also been a lot of work correcting a function so that it becomes Lipschitz. And the reason that it has privacy applications, and I don't know if Sophia's going to talk about this. Are you going to talk about it? Okay. All right. So I'm just going to say then that for Lipschitz functions, fixing a function so that it becomes Lipschitz, if it's close to Lipschitz and making it Lipschitz is actually interesting for privacy because the Laplace mechanism for differentially private release of functions works well on Lipschitz functions. And this means that even if your function is close to Lipschitz, you can run Laplace. It's close to Lipschitz, you fix it with a local method, and then you can run Laplace on it. Okay, so that was the idea of these works, and I'll say more later. Okay, so now the hope is that a local corrector for monotonicity might suffice because we're given a small efficient to evaluate description of the close to monotone function. By small, okay, for the game now is small means 2 to the root n. You might not think that's small, but then compare it to 2 to the n. It's a lot smaller than 2 to the n, right? So small, by small I mean 2 to the root n. Description of a close to monotone function g hat. Can we find a small, again 2 to the root n, efficient description of an algorithm that locally corrects the close to monotone function? And if I do that, then I can take, this is Bischutti-Timon. They gave me this close to monotone function. I correct it, like I give you this, I write down this circuit that's 2 to the root n size, okay? And it makes calls to this circuit that's 2 to the root n size that computes Bischutti-Timon. The whole thing together is 2 to the root n. And now it provides me input-output queries, x, g mon of x. This g mon that I get is monotone. Okay, and the whole thing only needed 2 to the square root n description. Okay, so the hypothesis output by the proper learner is what we got from Bischutti-Timon plus the corrector. And this thing defines a complete description of a monotone function. All right, so that's the plan. This is what you should remember. The rest is details, okay? All right, so how do we get local monotonicity correction in -2 minutes? How much time do I really get? 3 minutes, okay. All right, so I just, so why is it difficult even? I mean, I'm on the hypercube. So like maybe somebody asks me, is that supposed to be a 1? So I could like look around, I could do BFS and say, okay, everybody around me is a 1, so I'm gonna stay a 1. But maybe if I did BFS out further, I'd see some zeros. And then somehow I have to figure out, do these zeros become 1s or do these 1s become zeros? I don't know what to do, right? So it's not like obvious what to do. I mean, it can be done, we're gonna do it, but that's the reason why it might be a little complicated. Okay, so the basic observation is this. Okay, this is kind of the obvious observation, but just to make sure we agree on this. If I find a violating pair, so x is a 0 and y is a 1, that's a violation. If I flip them so that x is a 1 and y is a 0, then it's not going to get worse, right? Like it's definitely going to make me at least, it's not going to make me further from the closest monotone function. Okay, so that's one thing to notice. All right, but actually, a helpful idea is if I use a maximal matching, I can flip a lot of these monotonicity violating pairs at the same time. Okay, so now essentially what I want to know, okay, so I'm not telling you everything you need to know, but this is the essential underlying thing. What we need to know is, for each point, are we in the maximal matching? Did we get flipped or did we not get flipped? Do we stay the same? Okay, so that's kind of what I'd like to know. Yeah, in a global maximal matching. And I want to figure out, am I in a maximal matching? Okay, good. I want to figure out, am I in a maximal matching? So do I get flipped? All right, so I want to know, is there somebody below me that I'm matched to that I get flipped with? Okay, so now this is a very global problem. But really, I don't need to know who, I don't need to know if you're in the maximal matching or if you're in the maximal matching. I just need to know, am I in the maximal matching? So as far as I'm concerned, I just need to figure out, am I in the maximal matching? Okay, so that's now, the question is, can I figure out if I'm in the maximal matching in faster than figuring out the whole entire matching and seeing if I'm in it. That's the thing. And the difficulty is we need to maintain consistency. So I'm always in some maximal matching, right? There's always a maximum, but I need to decide that I'm in a maximal matching, and I need to be consistent in whatever my friend over here does and whatever my friend over here does. So we need to find there needs to be a global maximal matching defined, say, by a random string. It's like a short random string that defines for everybody what the maximal matching is. But then everybody needs to stay consistent with a maximal matching defined by that random string. Okay? So this is a model called local computation algorithms that we define, where we provide fast sublinear time queries to a large output. For example, is edge UV in the maximal matching? Faster than computing the full output. And the main challenge that Shafi mentioned is to maintain consistency without storing previous answers or any kind of work. So it's not like I don't get to, every time you ask me, I don't get to store what I answered and stay consistent with my previous answers. Okay, that's the main challenge in this model. All right, there has been lots of work done in this model. And these last two works here by Ghaffari and Wito and Ghaffari give us, this is like very nearly polynomial in the degree, and this is polynomial in the degree, maximal matching local computation algorithms, which we can just use to figure out, am I in the maximal matching or not? Okay, and I'm skipping a lot, but that is the thing we relied on. So I'm just trying to say what's the connection, because I am supposed to be done like a few minutes ago. So so what I just want to say is this can be used to construct a way of making this corrector algorithm based on maximal matching, and then together that gives us a local corrector from. What's that? Okay, so the original thing we iterated. Later, there was a simpler algorithm that we did something with this. We had a fixing procedure after the maximal matching that can be computed locally. And then you can just, okay, so that was, so either one can be made to work. What I just want to say is in the agnostic setting, I just want to say there's this really cool result of Jane and Arsen that was in the last Fox that actually gives you fully agnostic. What Arthing gave semi-agnostic, like a factor of 3 times opt plus epsilon, and they give fully agnostic. And it's a really beautiful algorithm where they give a way of basing it on low-degree polynomial regression via the ellipsoid method, and they use local computation algorithms to implement separation oracle queries, and that's all I can say. The rest you have to ask these guys how they did that. And then they also developed an L1 correction procedure. What I gave you was that was also, this is based on matching, this is based on matching in a different way. And this is essentially a generalization of the previous thing to L1 distance instead of just how many places you differ distance. Okay, so I'm just gonna say that's a great work. You should look at it, it's really beautiful. I think yeah. Always what? So there's some random bits. And fixing those random bits, it's always going to be the same G. So everything's going to be consistent. But there's some random bits that are global. And there's not that many. It's like.
How many is it 2 to the root n, or do you need like 2 to the n random bits?
No, I think it's polylog, right? It's
yeah, it's 2 to the root n random bits.
Is that many? Okay. Yeah.
Perhaps you already mentioned this, but what's the description of jihad that I return? Does it have a small description?
It's as small as the description of the Bashuri Tamon. So it's not smaller than that, but that's how small it is. So it's going to be 2 to the root n, yeah. And good. Also here. So this is, okay. So I just want to say a couple things. There have been other examples of LCAs used in learning. There was a work of Feigin and Shapiri that did inference in the presence of corrupted inputs, and they showed that the optimal learner strategy is a vertex cover local computation algorithm for bipartite graphs. And that was in turn based on a maximum matching LCA. So these ideas have been used in certain learning contexts before. And I think I'll stop there because I was just going to say LCAs have been used in dynamic algorithms and other algorithms and privacy, which I was going to say more about this, but I think I ran out of time. So, and I will stop at the thank you. Okay.
Final questions? Otherwise, we'll start setting up.